Welcome to the next episode of MiraCosta Ask an Expert. Today we have the honor and blessings of having Dr. Sorena Rahmanian with us, who kindly accepted our invitation to be the next guest of honor in our series. We're going to start right away with your question with the student questions. And some of your questions kind of give us a chance to get to know Dr. Rahmanian more. You all have seen his bio. Is so difficult when someone such as Dr. Rahmanian has such a rich bio and you want to condense it into a flyer, and you don't do justice to a lot of things that he has done in his life. So without further ado, let's start with your questions and we get to know him a bit more. Allow me to share the screen with you so we can see the questions. Dr. Rahmanian, who is Dr. Sorena Rahmanian today? How did a young man from Iran manage to get where you are today?
Hi, dear Sean.
We lost audio.
Dr. Rahmanian or Dr. Sorena. I'm very junior. I just rather recently graduated from my graduate program and got my doctorate. But, oh, can you hear me?
Yes, perfectly.
Okay, I guess this is not working. So yeah, just recently I graduated, but to just share a little bit of like who am I and where I'm coming from. I'm basically, well, so I actually just came to United States about like 10, 12 years ago from Iran. And in Iran, because of my religious background and being a Baha'i, I wasn't allowed to go to university and to continue my higher education. And the community, the Baha'i community there actually has arranged for a system of kind of like an underground education system. And I started that system studying computer sciences. But because I had aspiration for higher education, I decided to come here to United States to continue my education. And once I came to United States, I started exploring my path, career path and educational path in community college. Actually, not too far from your college, I started in Palomar College in San Marcos. And that was a great opportunity for me to explore my areas of interest, to see what are the opportunities, and kind of like to align that with my own interests and my own capacities. And after going through my initial courses in college, I came across my interest in biological systems and biological machinery, which is interesting because in high school, I did not like biology, and actually I tried to avoid it. But then in college, one of my friends suggested to take that course, and I really enjoyed learning about the intricacy of how molecular machinery works and how precise and complex is that system. And that's how my interest in biotechnology started. And after college, I transferred to UCSD, where I studied bioengineering and biotechnology. And there I got the chance to work with or learn from some of the leading scientists in the field of bioengineering and especially systems biology. And eventually, after working for a few years, I find my interest in getting more into data analysis and to basically developing computational tools for understanding biological systems. And that's how I decided to continue my doctorate education in systems biology or bioinformatics. And currently I'm working as a data scientist in a biotech company. So that's basically my educational or professional career in a snapshot.
Wonderful, thank you very much. So next question. There's plenty of questions I can ask, but let's go with the student question. I think we get to some of the wonderful things that you shared. Can you talk about your graduate research on metabolic networks?
Definitely. So that work actually was in University of California, San Diego, UCSD. where I got a chance to work with Dr. Bernard Paulson, who is actually one of the frontiers of the systems biology. And his work, in a sense, is very unique, and he's one of the people that actually opened up this field. If you go back to maybe 20, 30 years ago, he has books on system biology. He's looking at the metabolic network of biological organisms. And by metabolic network, maybe I can open it up a little bit. If you imagine any cell or cellular organism or any cell in your body, it's composed of many different metabolites or elements in that cell. And then there is proteins, which are machineries that take those elements and work with those elements to produce new elements or new material in your cell. So you basically can think of all the molecules in your cell or in your biological systems, and the reactions, all the reactions that are happening that transforming these molecules to other molecules. And you can create a matrix of all these reactions and all the material or all the chemical in the cell. And then you can do simulations and mathematical modeling to basically understand what happens when a cell is going through a disease state, and what parts of this network is actually under pressure. So yeah, at UCSC, I had the pleasure of working with Dr. Paulson, Bernard Paulson, who was one of the pioneers in the field of systems biology. And the area that he is focusing on is basically reconstructing a metabolic network for different biological organisms. So by metabolic network, maybe I can open it up a little further. If you think of any system such as a cell, it can be a cellular organism. There are many different molecules in that cell that is essential for the life of the cell. And there are many proteins, which are also part kind of molecule, but it's more kind of like a machine or machinery that can work and do the different works in the cell. And there's also a lot of enzymes that help different reactions in the cell. And if you think of all the enzymes that you have, they all are responsible for certain reaction. That is taking, each reaction is taking some of the molecules in the cell and turning those molecules to another molecules. So you can create a matrix of all the molecules in the cell and all the reactions that are happening in the cell. And that is kind of representing what is happening in your cell, all the kind of like livelihood that is happening in the cell. And you can ask a question of what happens if a cell is diseased and it doesn't have certain functionality, like certain enzyme or certain protein is knocked out and it can't function properly. There is a pressure point in your network. And as a result of that, you're gonna have like certain symptoms or certain lack of functionality. So then the question is, how can you shift this metabolic network to accommodate that? Then you can think of, oh, maybe if you use certain drug, that drug can help mediate this perturbation by affecting another part of the network. So you can do a lot of, once you have mathematical model, that matrix, you can do a lot of analysis to infer basically such relationships between the disease and potential drugs. And also you can think of it as industrial use of that. Like how can you also like think of bacteria that can generate certain biosustainable fuels, and then you can engineer those bacteria to basically like help with more biosustainable materials.
That's wonderful. Do you happen, if not, it is okay. Do you happen to have a copy of your dissertation? Can you show us the matrix? Did you create one for your dissertation, is it?
So yeah, actually, for my dissertation, I work on reconstructing metabolic network of human platelets. And I need to pull out the paper, but like maybe by the time like we are continuing our conversation, I can pull that out and just show a snapshot of that.
All right, perfect. We come back to that. Thank you very much. That's lovely. All right, next questions. See, you see why you're not alive? So many technical issues. All right. Your PhD degree in mathematical computational and systems biology sounds like mixing mathematics and biology sciences. Can you talk about the courses and research project you completed during your PhD studies?
Yeah, definitely. So yeah, it's exactly what it sounds like. It's a combination of math and computer and biology. So yeah, basically, I actually did take a lot of math courses and a lot of like differential equation, partial differential equation, and the purpose of it was the ability to model complex biological networks. Because if you're familiar at any level with biology, biology is not simple. It is simple, but it is also complex. It's different from engineering where you have complicated systems. Biology is complex in a sense that it has many layers, and each layer that you take off, there's more complexity within that. And somehow it's magically is working, right? So the idea is basically try to come with complex mathematical system where you can express this biological system with the level of complexity that it has. Because a lot of time, like you try to simplify things when you're modeling a physical phenomena, but the biological phenomena might require a little bit more complex modeling. So that's kind of like what this major that I studied, the mathematical and computational system biology, or in general, system biologists are more focusing on. And the courses that I took, I would say actually a lot of the statistics that I took, biostatistics, are currently as a data scientist, they are helpful for me. But more than any courses, I think it was the research itself that is handy. And it's not the information that is important, rather than learning how to get the right information and how to use that information. Learning how to ask a question. I think that's the biggest thing as a scientist you can learn, is how to ask the right question and how to go about trying to answer that question. And also like how to learn together. Because once you're pursuing research and you're pursuing a path of scientists, it's very important to realize that you belong to a community of science, and your understanding and your learning is part of that collective understanding. So being part of that community is also essential.
Wonderful, thank you. How important is it to know machine learning in data science?
Yeah, so data science is a hot field right now. So a lot of people, young people, want to go to data science. And hot points there is also like the machine learning. Everyone is about AI, machine learning. And a lot of time, as someone who is not familiar with it, it sounds like, oh, this like fancy thing, that science of like machine learning. But realistically, like all of us every day, we are dealing with many, many machine learning algorithms. And like whatever we do on our phone, like as soon as you start typing, there are machine learning algorithms trying to autofill it for you. Or when you're on Facebook tagging someone, there's machine learning algorithms that is at work. But really what it is basically looking at a lot of observations or a lot of data points and trying to find the pattern that exists between them and using that pattern to infer new data points. And that's basically statistics. That's what the statistics do. If you guys have done any kind of like math problem where you're correlating two things together, you're kind of like using machine learning. You're basically saying that these data points are always correlating to that. So if I have another data point on x-axis, I know what's going to be on y-axis. That's machine learning in a very simple form. But then, of course, there are many tools that have been developed for more rigorous type of learning and try to, as you've heard, like big data. We've been generating a lot of data. Internet has tons of data. So now, like having the computational ability to handle that data and to look at that data to basically strengthen your model is the question at hand when you're thinking of like what the data scientist needs to do. So yeah, machine learning is important, but also like how to apply the tools for machine learning, I think is a bigger part of it.
Wonderful. That's a wonderful answer. Thank you. You attended community college. You mentioned Palomar College. What courses did you take in college which still help you today in your work?
Yeah, so I mean, there are obvious ones, right? I can say like probably like linear algebra, like even like my calculus classes, all those things. Maybe you're not using the formula or the method, but the basic concepts behind it is still what is at work when you're trying to model something at a more complex level. So the principles is always the same. Same thing with the statistics. I think like the statistics is something that is always like coming back, especially if you're in data science or working with any type of like big data, having good foundation in the statistics is important. But as a scientist, I think one thing that helped me, and I wish I've been better at it, was writing. And that's something that maybe like I personally didn't pay attention to it, and like during my graduate school it came back to me, is how essential it is to be able to communicate with your colleagues, with your science community, and that comes from writing, and also like how you're organizing your thought in order to be able to communicate that. So I think that's one course that I would say is also like very connected, because sometimes as scientists, like initially we might like ignore it, but it is actually very important.
Wonderful, thank you. Next question. Was research something you always wanted to pursue, or did you find your passion for it by going down many paths?
So going back to when I came to United States, perhaps like the areas that I was very interested in was actually two things. One was like quantum physics, and then the other one was nanoengineering. And to be honest, the first thing I look up was like nanoengineering. At the time, when I started my education, UCSD didn't have any undergraduate degree in nanoengineering. And my friends suggested to look into biotechnology and bioengineering. And that's how I got introduced to biology. And I was fascinated by it. And that's kind of like the main kind of like critical point that I chose to go into bioengineering. So that was one major step in my path. And the second part of it was actually like after I graduated, I started working at Illumina. So Illumina is a company that is making almost like most of the sequencing platforms that sequence DNA in different environments, like it can be any laboratory or hospital, or perhaps in academic environment. And during my work there, I came across the fact that from the same results, two different scientists can come up with two different conclusions. And that was very shocking for me. And I thought that, oh, isn't science the same thing? Like you get one thing input, you should have an output, right? It should be the same output, but that wasn't the case. So I became more and more interested in the art of or science of understanding how to infer something from a data. And that's why I decided to pursue my higher education in the field of bioinformatics or system biology, where I gain more tools or get equipped with doing such analysis.
Wonderful, wonderful. Thank you very much. Right, next question. Now we're going to shift a little bit and look at the work you have done, and look at the nature of the work you have done. What does a protein engineer do, and can you share with us the nature of your work at Illumina? You kind of, indirectly address these questions, but please.
No, definitely. So, yeah, protein engineering. I think I introduced what the protein is. It's basically a molecular machine that does very specific work or does very specific job. So just like any machine, you can tweak it and modify it and make it better. So I did have actually like two different jobs that I work as a protein engineer. One of them was at a startup that they were designing very specific antibody. So an antibody and an antigen is basically like a key and a lock that basically you need to find the right key to a lock to either lock it or unlock it. And it is used sometimes for basically like curing a disease where you have certain foreign body like an antigen, and you want to have an antibody that is very specific to that. So as a protein engineer, your goal is to optimize the binding of this lock and key and how good they fit together and how fast it can connect to each other. So as an engineer, you start looking at the sequence because these molecules are built of smaller blocks. So you look at that block and you try to find the block that by changing them, you can increase their functionality. Similarly, at Illumina, the question that they were looking at the very heart of the sequencing, there's a protein called polymerase that is synthesizing the DNA, which is being sequenced. And that polymerase, its work is to add a block into the chain of the DNA molecule that you have. So at every time it adds a block. So the objective of optimizing that, or the engineering of that protein, is basically to make sure that it's putting the right block, so it's not making mistake, and it's doing it fast. And then you can also do all different kind of like engineering with it as well. So again, the same question of like, how do you design it or modify it so that molecule work better?
Wow, that's amazing. You can cure cancer that way also.
Well, yeah, I mean, a lot of this goes in that line, and our hope is that it will make it to there, but maybe a little bit at the lower level than dealing with the patients.
Next question. What did you decide to stop working and pursue your PhD degree? Why did you switch to data science? What aspect of data science interests you? I think you very much answered these questions, but I want to give you a chance to please.
Yeah, so that's a good question, because I mean, once I started working at Illumina, I should say it was a very good work environment. I really enjoyed my work. I enjoyed the work place itself, the culture, the people I was working with. One thing that's kind of like helped me to drive me to that direction. One was like the inspiration by the scientists that were working there, and seeing their capacity and desiring to be better in what I am doing, and to also be able to engage at a higher level with the research that I'm doing. So that was kind of like one main driver. And the other aspect of it was that I was very interested in dealing with data and analyzing data and modeling data, because I was always like interested in math, and the work I was doing was I always like brought it into my work, but it wasn't a part of the nature of the work I was doing. So those two were the main reason I was drive towards like doing my PhD in bioinformatics, and yeah, it's since then I've been enjoying it.
Wonderful, thank you. Next question. Can you share with us some of the recent data science project you worked on recently at the Creative Genomics? Can you take us through the steps involved? So if you have anything you want to share, I think you should be able to share.
Yeah, definitely. So initially I was actually looking into bioinformatics. So by training, I guess I'm kind of like bioinformatics, but these words are very connected to each other. So maybe to just like explain a little bit about that, bioinformatics is someone who is mainly making the tools for different type of analysis. And then the data scientist is someone who is using those tools and applying those tools to scientific problem or questions that we have. So in our company, in Cradle Genomics, we are actually like focused on diagnostics of fetal diagnostics. So basically, once we have a sample, I can just like explain maybe the bigger picture of the process, and then I can share like some of the projects that I've been working on. So once you have a sample, you're basically trying to separate the fetal cells from your sample. So there is a process that there are cell biologists involved with that. And once you got those cells that you're interested, you're basically trying to get to the DNA of those samples. So there is a whole process. It's called molecular biology that is involved with getting the DNA and purifying it from those cells. And once you have that, then you sequence that DNA, and that's a major third step. And then you have data. Then you have a bunch of zeros and ones to some extent. And at that point, that's where it enters the bioinformatic realm. And there are certain tools that we apply to digest that data, the zeros and ones, to more meaningful pieces, which is kind of like more, it's like kind of like sentences that are read out of the book of the DNA of that sample. And then the data scientist takes those sentences and try to understand what is the underlying, is there any specific challenges or any specific abnormality with that sample, and trying to look for those. So that's kind of like where the data scientist is involved. But also a lot of it is also like trying to understand how the downstream processes, the sample collection, the sample processing is affecting the data and the integrity of the data that you're getting. So a lot of the work of the data scientist is also making sure that we are having a good process, because I remember one of my mentors used to say, if you have a garbage in, you have a garbage out. So you got to make sure that what you're getting and working on is a good material and good quality. So a lot of the work is also like trying to identify those niches. So one of the projects that I'm working right now is comparing like different methods that we are using to prepare and to extract the DNA from these cells, and see if these different methods are affecting the data at the level that we are seeing in a different ways. So usually in a DNA, you have about like 3 billion base pairs. And once you sequence your samples, you can see at each point of your 3 billion, it's like a 3 billion sentence, right? At which point of it, you have higher or lower coverage. And using the different methods can affect the biases that you have in your data, and being able to detect which biases will affect your diagnosis is the question that the data scientist will look at. And you can use many different tools. Some of the machine learning, mostly at the beginning, you use unsupervised machine learning to see any clusterings of the samples and see if there is any difference between the two methods. And then you develop some hypotheses, and you can go after those hypotheses, exploring it further.
So basically, by having data, you could have divided the data. You use some portion of it, you create this model, or using machine learning to create a hypothesis. Then you use rest of the data to test that hypothesis.
That's usually like the machine learning story comes like that you partition your data, you use some of it to train a model, and then you apply that model to test the rest of your data to get the accuracy of that model. And
it's also constantly you have to communicate with the other protagonists in this process, because someone who sequenced the DNA, maybe they had a faulty system. So if you notice abnormality, you need to communicate it with them to make sure it wasn't in the process. Or even the sample that they got from the fetus, or however they collected, maybe there was so constantly it's requiring you as a data scientist communicate with all these different.
That's the beauty of it. Like you're given something and they say it's X, but never trust that it's X. Because that X has a last name and has a root, and you can look into how that X becomes X. And there is usually a lot of things beforehand that has affect the data that you're getting. And that's a big part of like a data scientist, to make sure that that X is really X.
Yes, thank you. We lost Marisha for a second. Yes, this is my internet. This is so embarrassing. Oh, there we go. Probably back. Yes, very perfect. Thank you very much. So, yes, never trust what you're given until you investigate it.
It's like in your internet provider tells you this is a 50 megabits per second internet.
It's not. Check it is not. As you can witness in our dilemma right now. All right, wonderful. Thank you very much. Next question. As a data scientist, how important is it to know the discipline or context of the problem? Can a data scientist help a team make a data-driven decision without knowing the fields or the origin of the data? How can you gain real-world experiences?
So, yes, as a data scientist, you can apply your tool to whatever they give you. However, I think there is a great value for the data scientist to make himself or herself familiar with where that data came. Just as I was saying before, like that X that is given to you is usually not X. And if you don't have the familiarity with the process that went into it, it might be hard for you to detect that. And usually in the daily routines, people just give it to you because like they think it's X, but there is a lot of other details that you need to ask questions, you need to interact with the people. Sometimes actually you get to actually go and shadow them and see what they are doing and then ask questions and try to understand. Because again, like the data doesn't just appear like that. There is the way that the data has collected has a lot to say about what the features that you are seeing in the data. And especially when you're looking with anything biological related, you gotta make sure that you're understanding what that data is that you're working on.
Brilliant, thank you. That's a wonderful explanation. Next question, what makes a data scientist a mature data scientist? How can inferential statistics be useful in data science?
Well, I don't know, we should ask a mature data scientist.
Where did you come up with that term, mature data science?
No, that's a good question. Again, like I think like one of the things is that you can always make a statement as a data scientist, and you need to make sure and understand the consequences of the statements you're making, and make sure, because everything has assumptions with it, to make sure that you communicate well what are the assumptions that goes with it, what is the confidence of the statement that you're making, and what is the domain that the statement has and that is correct. I think as a mature data scientist, you don't just find something and like give it out, but rather you make sure that your finding is accurate, and there's a saying that no model is perfect. Some model is useful, right? So the same thing, just be aware that what you're presenting as your result is useful to a certain extent, and making sure you communicate that well. I think that's a good like maturity of a data scientist, to the level I understand.
That is beautiful. That is beautifully said. I think that actually is one of the questions coming up. Next question, based on your experiences, can you unpack data-driven problem-solving skills?
Wow, that's an interesting package. So actually, a lot of the tools that we use comes in packages. Usually they have a manual, so you can read it. That's great. But one thing I can say is a lot of time, like traditionally, especially like biologists, you had a very specific hypothesis and you were looking at one specific point, and you would come up with the experiment and design an experiment, and you apply that to get your answer. So you probe what you think is the hypothesis, you deny it, or you basically accept it that it's the right hypothesis. But when you come to a data-driven world, it's a little different. It's kind of like you're not making any assumption. You're taking all the observation and all the data that is available to you, and you try to infer certain relationships, and then perhaps then you will see some hypothesis, and then you can test that hypothesis. Just as you said, you create a model with some of the data, then you apply that model to the rest of the data, and then you measure the accuracy or the domain of that model to see how accurate it is.
And that actually brings us to the next question. Why do you think roughly 85 to 95% of data science projects fail or never make it into production?
Oh, that's a good estimate. So actually, I remember when I was at Illumina, there was one of my colleagues. He was also, I think, in the data science part of our group, in protein engineering group. And I remember vividly, like one of his presentation, he basically shared a website with us that it had examples of completely random events in history, two different part of the world, two different time zone, like different generations, that perfectly correlated, the data points from those two events perfectly correlated with each other. So it's a big trap, right? It's very easy for data scientists to see something like very beautifully like correlated or like very beautifully explained by a model and like jump at it and say, hey, I find a cue. but again, that's a maturity to understand that no, every model has its flaws, and trying to understand that. So I think the reason that a lot of time it fails is because of that immature conclusion that hasn't been tested enough. And we are always like, we are in rush, we want to find the answer, so we jump at the conclusion, but like a lot of time it turns out to be wrong.
That's brilliant. I can share that with other statistics students. So there's a section that talk about the causation versus correlation. So never draw a conclusion. Thank you very much. That was brilliant. Or as I'm taking time, so now the nature of question is shifting a little bit. Look at some equity. Did you face any discrimination or hidden biases during your studies or during your professional lives? How did you overcome them, and what drove you to persist?
So in my earlier education, definitely, like again, as I mentioned, like as a Baha'i in Iran, like there was systematic discrimination against Baha'is, and definitely I think that was kind of like a challenge. But at the same time, it provided opportunities, right? Because it provides opportunity. For example, it makes that community that are being discriminated much closer and stronger and more resilient to that discrimination. And that being said, the discrimination is always there, no matter where you go and how. Even like in an environment that is healthy, sometimes like you see those discrimination just because of personal preferences that people have, and unfortunately in a lot of systems there is that hierarchy that those personal preferences makes it difficult for some people compared to others. But again, like there's always friends that can help, and just being able to rely on someone who also understand you, even if they are not going through the same discrimination or same challenge. But then also like relying on the fact that you have the capacity to overcome that and to be bigger or to be higher than the person who is discriminating against you. If you are bothered by it too much, then you are going to be trapped in it. But if you lift yourself above that, you're going to grow higher than that.
Thank you. That's well said. Did you ever feel underrepresented in the field you're working at? Did you ever feel like minority in the field?
I don't know if I can say that, because I think in bioinformatics, I see a lot of like guys usually. So as far as like, I think the gender part of it, like there's usually a lot of it. Interestingly enough, actually, the lab that I was working in my graduate school, it was majority like females in the lab. And it was interesting because they were feeling that in the larger society of bioinformaticians, there is usually like some discrimination, and that is very true. But yeah, again, as I said, like the community that is created because of that is helping to overcome those challenges, and the challenges are always there. So it's not a magical thing that goes away.
So you just gave us the idea. So maybe the next guest that we will have for MiraCosta as an expert would be a female data scientist, and how they overcome.
Actually, one of my friends, maybe I can refer her. She actually came from Mexico as an international student to do her PhD in bioinformatics. So I think like she probably can be a good
oh, that's lovely
person to talk to.
Is she working in the field right now?
Yeah, she just graduated this year, and she's working in LA, but yeah, she's working in bioinformatics field.
Oh, perfect. Can you introduce us? So maybe we can.
Yeah, definitely.
So that's lovely. Thank you. So gender is one thing you notice, but when it comes to ethnicity and race, do you see more diversity in data science field than, let's say, chemistry or other sciences?
I mean, our lab was pretty diverse. We have people from all across the globe, and I think again, like also like in our work, I see a lot of diversity. So I would say, yeah, data science is actually like has a good diversity of people in it, ethnicity wise and nationality wise.
So everyone, that's a field to explore. MiraCosta is working on creating our data science program. That actually brings us to the next two questions. Talks about some of our students and our data has shown are marginalized. So for instance, one of the student population who data has shown be at risk are students who are older than 25 or they have children when they come back to school. Mm-hmm. The next question is a little personal, so feel free not to answer it. Do you have any children? What advice do you have for students who want to start a school after 25 or sometimes with children?
Mm-hmm. So I don't have any children. I did start my graduate school after I was 30, so I can talk about that. But I can also share like one of my good friends during my PhD. He started also when he was older than 30, and he had 3 kids when he started. And it was difficult, I'm not denying that, but he did it, and he managed to attend to his children and family and finish his PhD. And actually a lot of graduates, it's very common for graduate students to have family and have kids. Most of my lab mates actually got married and just have kids right before their graduation. And as far as the age goes, I think most of the people in graduate school that I came across, they are probably around 25 and above. So there are a lot of people who might start earlier, but it's very common to start graduate school at a higher age.
Perfect, thank you. Some of our student populations who have been disproportionately impacted by a lack of equity and diversity in higher education are from historically marginalized communities. As a scientist, as an educator, scholar, how do you suggest we can bring diversity into a STEM field?
Mm-hmm. So, I mean, there is 2 key elements, I think. One is like helping and working with the system that we have, the graduate school, and to help it to be more welcoming. Because a lot of time it says like, we don't discriminate, but then not discriminating is not equity. You need to make it accessible to the same level. So if someone is removed from it, you need to make it more accessible to them than someone. So I'm thinking of like someone whose dad is in a data science. It's much easier for them to access such a program and to go there versus someone who is the first generation who is going to college, then you need to actually make more effort to make it. That's the true equity. And the other aspect of it is actually working with the individuals themselves and trying to overcome certain dichotomies or certain obstacles that are mainly also like part of it like is mental obstacles of understanding your capacity, because a lot of time we undermine what our capacity and abilities are, and we say, oh no, that's not for me, that's for someone else that fits certain areas. So helping individuals to understand overcome that obstacle, I think, is one part of the solution, but then also like working with the school system to be able to make it accessible as well.
Well said, thank you. And then make sure we have addressed all this in questions. Yes. Did you by any chance find your dissertation?
For my master's or for my PhD?
Both.
So yeah, maybe I can share. Maybe I can share. Maybe I can share my paper from my PhD, or actually, like maybe I can just share the dissertation. I should have it too, because I haven't changed the laptop since then. So I can just share the dissertation as well.
Thank you very much, David. I know they're pushing the limit to 1 hour, so appreciate it.
So here we go. Do you want the actual like the paper or the presentation?
I think presentation would make it easier.
Presentation for sure. Just a fun fact, the actual paper, it probably went through like 40 something revisions before it ends. As a graduate student, I think you get very used to that, but it's a lot of back and forth between you and your professor to get through it. And yeah, so I'm gonna just share my screen. And I don't know where are you guys able to see my screen?
Yes, I see a lot of coding. Now, perfect. Now we see the presentation.
Okay.
Embryonic development is highly coordinated.
So yeah, basically these are my thesis projects, and the main 3 projects that I've been working on. So I did a study the embryonic development of mouse, and specifically looking at these small RNA molecules called microRNAs that they regulate the expression of different genes. And if you think of it in the short matter of only a few weeks, a number of cells, few cells will become a full organism. And if you think there is a lot of changes that needs to happen, and these small molecules, these microRNAs, play a critical role in making those changes and regulating those changes. So I did spend majority of my PhD studying that, and that work actually got published. And if you guys are interested, you can look it up. It's called Dynamics of MicroRNA Expression During Mouse Embryonic Development. And then most of my recent work was actually coming up with a new technique of looking at the RNA molecules as they are being made. Because a lot of time when you're looking, or you have techniques that are studying different RNA molecules, you're looking at a snapshot of what molecules are there. But the technique that we've been working on was how to detect which molecule has been made recently compared to a molecule that has been there for a while. That gives you a sense of where the state of a cell is moving to. Because as you know, during that early stages, there is a lot of changes, quick changes. So it's critical to know where you are and where you're going. Like if you can imagine of a vector, like the direction of the vector. So the idea of like trying to identify like recently made molecules, and that's what I'm referring to as a long toxic toxic stands for thiouridine. It's a specific molecule. And that was kind of like the second part of my thesis. And the last part was applying these two methods to a specific cell differentiation and see how the two of them are related together. So actually, maybe I don't know how much time you guys have. Just fun.
Please continue. We have plenty of time. Are you kidding? This is lovely.
Yeah, just a fun biology video. This is actually a one mouse cell. This is from a university in Japan, and they have captured how the evolution of this one cell to a whole organism or whole embryo. So it's a fun, and it's capturing the time, how fast it's developing. It's interesting to see how quickly suddenly like different like hearts emerges and brain emerges, and then also like the scale, how quickly it grows. So I'm gonna just play it. I think it's like maybe 1 minute or so. So this is kind of like going, how fast is the speed? So now it's like 2 days, 3 days, 4, 5. It's still a bunch of cells, not much. 6 days, you suddenly see a shape, and then 8 days, 9 days, and then eventually, like there are like organs that are emerging within like 12 days and becoming functional, and you get blood circulation, you get eye, and the scale is right now it's 2 centimeters, which is 1 inch. Now it gets a little bigger, and that becomes the embryo that is ready to come to this world, right? And this is kind of like the different levels. So at within like within 7 days, you start having some neurons, and then at 8 days you're gonna have like heart formation, and then 9 days you start have some limbs, and then kidney and liver and lung. So it's a very dynamic process, and understanding again, as I said, biological systems are complex and there are layers. So understanding what is happening underneath that is causing a heart to form, that's the heart of like the questions that we were all exploring as part of my graduate work. And one thing as a data scientist I do and I enjoy is graphical presentation or visual presentation of the data. So this is something called joy plot, which is basically overlaying multiple like density plots of different stages. So this is basically the expression of tissue-specific microRNAs over different days of the development, from 10 days to 16 days. So as you can see, as the development of the mouse goes forward, you have more and more tissue-specific microRNA. So at the earliest stages, you have global microRNAs that are regulating everything similarly. But then as your mouse is becoming more and more mature, up to like P0 is when it's like born, you get more and more specific microRNAs that are specific to certain tissues. So you have microRNAs that are specific to heart, or microRNAs that are specific to liver, and you get more expression of them at the later stages. And this is like one of the figures that we were working for. But there is a lot of, I really enjoy like the graphical representations. I'm sure you guys are familiar with something called heat map. So this is also like looking at the expression, spatial as in like the different tissues. So these are different tissues that we studied, and then also different time points in the gray scale. And these are like different microRNAs that have been expressed at these different time points. And another fun fact is, as a scientist, you get to work with many different people. So I think there was about like maybe at least 10 different groups across United States that help to provide such data that we were working on. And you get to interact with them, you get to hear from them, their opinions, and like have that conversation and consultation with them in order to make the work mature and ready for publication.
That's wonderful. Can you share with us? I want to continue with this graphical representation you have. What does a raw data look like? What did you get from those sources? Do you have that handy by any chance?
Oh gosh, I don't even know if I remember my login.
Oh, it's okay, don't worry about it.
But I can probably I can probably try to find. No, I'm trying to.
So you use R to do a lot of your analysis? That's wonderful.
Actually, yeah, maybe I can share my screen. So one thing which is beautiful about like today's, let's see if I can find it. It's that you have access to the dynamics. You have access to the work of people, right? So like you can actually look it up and like you have access to find it. So you can like read the paper about like what I was just showing to you guys here, but then also you can find like supplementary materials. So these are not quite raw data, but we can maybe take a look at a couple of these things. So this is like basically like the data behind one of the graphs, and it's basically like the correlation of the or the targeting relationship of the couple of the clusterings. And let me see if this is the. I think this is mostly the methods and figures, so that's not it. Oh, actually, if you go to the paper, there should be a table of the supplementary material that we can look at what we have there. Maybe they don't have the paper there, the supplementary material description there. If it was my work computer, it would have been probably easier for me to pull out some raw data to show you. Do I have you or did I miss you? Yo, Habibi. Ya Habibi.
Can you hear me okay?
Yes. Habibi, you're darker than my terminal.
It's fascinating. My
Oh, here you go. You can. So yeah, I managed to find something. This is not my like quite data, but can you see my screen?
second moment. I don't have. And this is a laptop I got from work. I can connect my. Can you hear me now?
Yeah, I can hear you. Can you see my screen?
Yes, I can see your terminal. Yes.
Okay, so I finally managed to find something, and to be this is not like a data or sample. It's like type of data that I've worked.
This is RS Studio.
No. This is like a terminal. This is like a server. So I'm on a server.
Oh yes. Okay.
But I'm just gonna show you guys. This is called like human genome reference. So this is basically like the genome of human. So as you can see, like these are like sequences, right? So G, T, T, A, C, T, T, G, G. So a lot of the data that sometimes like we are working with, and this can goes like for pages, right?
So this is DNA sequencing.
Yeah, so these are DNA sequences. These are references. So basically, actually, each of these, you see how it starts with the greater than sign.
Yes.
So each of these is a reference for a specific microRNA. You see MIR1302. So that's a microRNA. So this is the sequence for that microRNA. And then there's sequence for another microRNA or another link RNA. So each of the genes are potentially included here. And this goes for, I can tell you, it's going to take a while, but it will tell you, yeah. So there is about 5,000,007 5.7 million entries in that file.
704,000. Oh my God! Let's connection. Yes.
Yeah.
Wow.
So then, like when you're aligning your samples, you're basically looking for each of the reads. Where does it match? So it's basically you're trying to kind of like match it, not manually. Of course, there are tools that you use, but that's the very beginning of the work that you do, and then you build upon that. And
yes. And looking at that amount of data, do you hear me? I think your connection. Yes.
Okay, so connection is bad at this point.
I think both of us have the same problem. So when you could do this.
Sorry, what was it?
A huge amount of data, so it takes something days. Am I correct? So looking at this is a massive amount of data. So when you do analysis, it probably takes days.
Well, it depends on what type of data you're working with and like what you're doing. And this is kind of like we can look at maybe actually let's do. So this is some like simple code that you do to work with reading specific files or doing things, and you make a whole bunch of these little codes trying to do your work.